everyone. My name is Tasneem. I'm the Senior Manager at 98 Percentile in the HR department. And today we did a wonderful drive with XLR. It was amazing right from the very beginning, from the very first day when I got in touch with them till today. I think it was an extremely smooth journey with them. There were multiple follow-ups done by the representatives in order to check that we would be, what time we would be coming, how many people would be coming, what vehicle we would get. To that extent, they were so precise in giving all the information to us. It was extremely great to get associated with them and have a drive at XLR campus. So we are very, very happy that we got a chance to do this. Now, coming to the students, what XLR had, I think they were extremely enthusiastic. They were well prepared. They were aware of what they are coming for. I think there was some back-end preparation which they did that was commendable. They also were very confident and they were open to any kind of thing we were asking them to do. That was I think the best part. Now, I really hope we have a very, very fruitful association with each one of them and XLR in future. We are really looking forward to have many more drives like this.
Hi everyone, my name is Prachi Sharma and I'm the Senior Project Manager for IT Department at 90th Percentile. So today we were here for this IT bootcamp, right, this technical drive and at XLR. So it was a great experience and I would feel that the students, they are the freshers, right, but it doesn't seem like that. So if I talk about their technical and cognitive ability, they all seems pretty good in that and that's what I felt. And I guess they have been taught pretty well at XLR, so that's how they have performed good in their aptitude and the technical tests. So I wish them all the best and it was a very great experience over here.
Hi, this is Patan, Technology Consulting Manager from 98th Percentile. We visited XLR for the campus placement drive and it went very well today. Miss Ambika, Miss Pragati, everyone received us greatly here and we had a lot of enjoyable time here. The students even had great experience with us. They were interactive, they had good aptitude and all the technological skills they showed. I think they were all well and we really appreciate their time that they spared to us and I think we will be doing a great job. We are expecting a lot of people to be hired from them. Let's see. it was a great experience altogether.
Thank you.
Thank you so much.
From entering into the cyber tower to exiting out of this tower, the XLR team has been received me with such a care and pleasure.
I am the part of this XLR since 4 months. From the third month itself, they have conducted the placement sessions from the third month itself, and this is the fourth month, and this is the 90th percentile is one of the placement drive I have attended so far, and attending to this drive is such a good experience for me. All the HRs and the team made us feel very comfortable and confident.
XLR helped me a lot, and I experienced a lot of things today. So I'm really hope to be placed in that company. I'm confident about that. Thank you.
This was my first association with XLR. I had got a call from Miss Shubha, and we fixed a drive here. Today when we came here, I was not expecting much, but the hospitality was too good. Staff is quite cooperative, and it's like a happy-go-lucky kind of a environment here when it comes to XLR people. When it comes to candidates, yeah, we have got few candidates, and they are all agreeing to all our terms and conditions, and I hope they join the organization and work for us, and I'm expecting long-term association with XLR people, with more recruitments or more collaborations with them.
XLR has been a good partner for us because we found some of the candidates were excellent, and we wanted people with good business experience, not only just the Java or whatever full stack development or whatever they were being trained on. They were also people with a good background knowledge, and whom we have really shortlisted, and we assume that they are going to make a good career in BusyBrains.
XLR arranged our placements for the BusyBrains company. I felt good. I hope that it will be positive for us and change our lives in IT sector. So thank you, XLR.
Hi, my name is Revant. I joined XLR's course of data analytics. While the course was going through, the faculty were very good. They were guiding us really well, and they were providing in-depth insights of the industry. We were taught the latest things. We were taught what the industry needs, and after that, post completion of my course, we were going through a live project where we were facing real-time scenarios, and we were encountering all those scenarios which we would be encountering in a job. We completed the project, and we got through a certification which stated that we got a data analytics certification from XLR, and after that we were placed in mock interviews, and they also gave us how the interviews are and how tough they are. The interviews were really good, And post completion of the mock interview, they started placement drives. Today is my first placement drive in a company called Busy Brain. I really want to thank XLR for providing me this opportunity, and I'm really hoping to see much more opportunities in the future. Thank you, XLR.
When I came into XLR, the learning experience was very good. Today there was the interview session from Busy Brain's company. The interview session went extremely well. I got to learn many new things. Thank you, XLR.
My name is Almas. So I'm here to do a campus drive. I'm coming from a company called Dotline. I deal with HR and operations, and unexpectedly I got a call from Ashwin sir. So he was saying about XLR solutions and the way he approached us, saying that the candidates will be trained as per our requirements. So digital marketing was the immediate requirement. We have gone through the interview process. It was quite excited to see good number of talent pools in XLR. We could shortlist couple of them, and we have given some placements as well, even both for the full-time as well as internship. So overall our experience with XLR is nice, and we look forward for a long-term relationship with XLR and the excited team. Thank you.
Hi, my name is Rupesh, and I work with Dotline as a performance marketeer, and I've got about like 15 plus years of experience. So today I happen to come here for the placement drive. Rightfully matched few profiles based on the requirement that we had. I'm so happy that XLR did a great job in terms of getting the pool of talents out and training them, and lucky that we are here so that we got the right match and we were able to get it. And thank you so much, XLR. Thank you.
So hello guys, myself Mohammad Tarhib. I am a graduate from aviation background, and then I thought of doing my course in digital marketing. So then XLR was the best opportunity for me. I took out digital marketing from them, and then I enhanced my skills in digital marketing. They offered me a campus drive in a company called Dotline. They gave us 3 days of good session for student development program, wherein they gave us a good opportunity of learning whatever the skills is required for the interview, for us to enhance our skills and then perform well in interview. So yeah, after the interview went well and I have got selected in Dotline Designs right now, and I am excited for the opportunity coming up.
Hi, I am Pinky. I did my MBA in HR. How I got to know about this institute is through Google. And then we got a wonderful trainer whose name is Azhar. He used to give theoretical ideas, and for this interview, we had a prior 3-day session for just brushing up all the requirements needed to attend the interview, which is again a wonderful thing from XLR team. So I had a good experience in attending the interview session for Dotline company. Thank you.
My name is Rahul Ulkar. I'm been working as a senior architect in UX systems. So today we are here at XLR Systems for the placement drive, and I really appreciate the placement services that the team that I actually met. We really got a good service and hospital service actually. They the way they actually.
Sir, two less people are there. Shall we wait or shall I start? Amar sir?
We can proceed, sir.
No problem, no?
Yeah.
Okay. Okay, so let me share my screen. Okay. Right. Correct. So good evening, everyone. Welcome to the session on agentic AI and generative AI. So this is day 9 of our session, right? Particularly last couple of sessions, 3 sessions, I would say, we have seen more practical component. So I will continue with that. Just let me share my screen. Okay. Right. So let us see, or let us start with the important part. The next, one of the important concepts in generative AI is the concept of TF-IDF. So, in the last sessions, we have covered a few topics. So in continuation for that, we are going to see this concept of TF-IDF. Now, what is this TF-IDF? Okay. So to understand in a normal definition, or you can say, let us try and see the full form first, right? So the full form of TF-IDF is term frequency inverse document frequency. So this is, the full form of basically TF-IDF. Now, what this will do? Okay. So this TF-IDF, right? It's a model, or we would say it's a function, right? This basically evaluates a document. For example, a sentence. Okay, let us not talk about a document. Let us say a corpus or a sentence, right? Or a group of huge sentences, or a big kind of corpus. So it evaluates each and every word in the corpus. So that is the task of using this TF-IDF. So where this is used, so I have, by this name itself, you would have understood that this is basically used in multiple places, right? For example, like text mining, document ranking, information retrieval, feature extraction for machine learning, and much more. So let us see what is this TF-IDF is basically about. There are two components when it comes to TF-IDF. The first component is the TF part, and then the other part is IDF part. So what this TF will do is, this term frequency will count how many times a particular part has been repeated. That is the TF part. And the IDF part, inverse document frequency, will basically apply the logarithm for the TF part. Okay. So log of 1 plus number of documents divided by the 1 plus df into t, right? df of t plus 1. So this is the formula which this IDF and TF actually applies. Now let us see this in bit more detail. Okay. So if we, this is just a basic formula, right? Now let us understand that what are the things which are, in that. Now, when you say TF-IDF, it's actually a product, TF into IDF. Now, what is the TF part? The number of times the term appears in the document, that we have already seen by this, count formula. So number of times it appears divided by the total number of terms in the document. So it is basically like a probability, right? So how many favorable cases divided by the total number of cases? Exactly, this formula should ring you, a bell, remembering that probability formula. So number of terms, right? Number of times a particular term is repeated, whichever term you actually want, divided by the total number of terms in the document. Now let us see what is IDF. So IDF is logarithm of number of documents in the corpus divided by the number of documents in the corpus containing the term. This is what basically the TF-IDF is. This basically calculates the probability in a single sentence, that how much frequency or how much possibility is there for a particular term to occur based on the context, right? Best example, in mining a particular document, information retrieval, by this probability, it will try to predict which or we can understand that what is the important part in that particular document. Okay. So again, coming to the simple formulas, I've just put a few formulas where you'll be trying to understand that what exactly is this TF-IDF is about. Okay. So this has a bit of formulation. Okay. So it's like a mathematical formulas. Okay. Let us not think too much or break our head in formulation part, because just this concept also requires you to understand that these are the kinds of formulas are there in this particular concept. So instead of just skipping this, I just wanted to show you as well. Now let us go to the real world analogy, that how we can understand this TF-IDF. Okay, so imagine you're scanning thousands of new articles. Words like the, is, and appear everywhere and they are less informative. There is a technical term for that which is called as a stop words. So words like inflation, quantum, Elon Musk appears in specific articles. These are more informative. So it will try to segregate what is important, what is not important. Now, see the last line, which will give you more understanding about the TF-IDF concept. So this TF-IDF boosts the weight of rare but meaningful words while downweighting common ones. So it is basically highlighting or giving importance to the words which give more meaning to the sentence. That is how a model can be built, and when the model is built in a proper way, right? So the stop word should not give lot of weight, or weight is nothing but importance, right? So the important words, or so I can say the words which are key in building a model should have more weight. That is what is this TF-IDF concept actually does. So, right, so that is about TF-IDF. So we'll see that practical part also about TF-IDF. Now let us go to the next important concept. This is actually a really big concept, I would say. Okay, there is a lot of I'll try to make it very simple, particularly in the word embeddings, because there are a few models like the word to vector, glove, right? And I'll go one step and the other we will go. First, let us understand what is word embeddings. Okay, so after word embeddings, word to vector and glove, both practical part also we will see, because there are two important models, right? Many more are there, but these two are also very important. We will see that also, okay, along with the TF-IDF. Now, let us see what is word embeddings, right? And what is the concept behind this? In a simple terms, right? Representing the words as vectors is what word embedding is. Okay, so in a simple, this is basically, those who have studied bit of math, okay, so will understand, in an easier way, right? They will understand very easily this concept of word embeddings. So what is a vector, right? So now it's actually, something can be represented in a continuous form using the scalars and the variables is what a vector basically is. Now, this word embeddings or these words will be represented as a vectors, okay, in the vector space. Okay, so this vector space is nothing but a collection of vectors which can be formed, right, in the form of a vector, right? So why this are actually used is, or why this vector form is basically used is to identify the similarity between the words and also to map the words. For example, if you're searching for a particular aspect, that particular document or that particular article, something like that should come up, right? So for that we need that mapping, right? So for that we are going to use the word embeddings concept. It is extremely important concept in the whole generative AI part. So wherever you see generative AI, you will see this word embeddings. Okay, so this is not like a one-hot encoding and all. What this actually does is this captures the context and the relationship of the words. Okay, the first and foremost concept, where everything has started, right? Or this corpus, using the corpus and starting to build the words, right? And building the models in a way to actually predict, right? Everything started with the concept of word to vector. Word to vector is actually designed and constructed and formed, or found, or research is done by the Google Brain team. Okay, there's a Google Brain team, so they have done this or designed this word to vector. Then we have one more concept, which is glove, right? So glove is nothing but global vectors. Okay, so word to vector as well as glove concept, both are extremely important. After that there is fast text. Okay, so fast text is it is good, but we are not going to see that. We will see word to vector and glove, and we'll see contextual embeddings like BERT, Elmo, and GPT. So these are based on attention mechanism and transformers technology. So we will see the practical part of attention mechanism as well as the transformers using these BERT and GPTs and Elmos as well. So before that, let us also understand about what is this word to vector and glove, because they are the base for framing or understanding of I would say attention mechanism and transformers. So we will also try to understand also what is this attention mechanism, why it is playing a very important role, particularly in the field of transformers and generative AI. Why, how transformers is being used in generative AI. So that is the interesting part, no? That how in generative AI transformers are contributing. So if you have to understand how transformers are contributing, you have to understand the attention mechanism. So if you want to understand the attention mechanism, you have to understand the LSTMs, right? So LSTMs you have to understand, and then after understanding LSTM, you should understand what is bidirectional LSTM, right? All those things we will see the practical part along with the theoretical concepts. So the bigger picture now in the generative AI is the transformers. Transformers are designed from the attention mechanism. It's based on attention mechanism concept. From attention mechanism, this LSTMs, it is designed from LSTMs and bidirectional LSTMs. And bidirectional LSTMs and LSTMs are extracted or designed from glove and word to vector. So that is where glove to glove and word to vector are playing a very important role, right, in the whole picture and the scenario. So now let us see where these word to vectors are basically used, right? Not just the word to vectors, I would say on the whole word embeddings where they are used. So by this time you would have been aware. So text classification, named entity recognition. So we have seen the practical part also on the named entity recognition. Then we have the machine translation, sentiment analysis, Q&A, question answering, chatbots, and language modeling. So what are the benefits of using the word embeddings? So what are the benefits of using this word embeddings, right? So this reduces the input dimensionality, right? That is one thing. And this actually captures the semantics and the syntactic patterns. Okay. This model helps generalize better, and it also improves the downstream. So all these aspects are contributing to the generative AI what we are using in the current scenario. So next is the limitations part. So what are the limitations for this? So static embeddings can't distinguish polyphony, right? So animal versus cricket, which is bad, then can encode biases from the training data. Then contextual embeddings are more powerful but computationally expensive. So, understanding what are the benefits, what are the limitations, you will understand better when you try to, see the practical part. More, understanding will be there in that aspect. Okay, so let us not too much touch on this now. So, on a simple note, to understand what is word embeddings, one word I really liked in the sentence is word embeddings revolutionized NLP by allowing machines to understand the meaning and relationship between words. That is why only if we give something in a GPT model, it is able to understand what the user has given, because it has that word embeddings technology inside that. So it is able to understand what the user is actually asking or what the user actually wants. So this has actually revolutionized, or I would say this has, transformed the way we are actually now looking at, right, when it comes to the AI modeling, right, or artificial intelligence in a bigger picture, right? Because generative AI is, something which is developed very recently because of these all the concepts what we are using, and contributing to this generative AI what we are using kind of right now, this word embeddings also play a very, very, primary role. Okay, so they're foundational to modern NLP pipelines and are must know concept for anyone working on AI and language understanding. So that is what it makes very important, and more focus is required on the concept of word embeddings. So now let us see the first one, which is the word to vector. So word to vector, right? I told this is actually designed by Google. So word to vector is a neural network based model that converts words into vector representations. Okay, so when we say word embeddings, the word embedding means we are saying word embeddings now. This embeddings actually mean that vector representation. It's a pure math concept which uses the concepts of cosine similarity, right? Models, right? Such as functions like the cosine similarity and all. So how it will identify is it will try to understand the similar context which have the similar vectors. So who has discovered, or I would say research has been done by Thomas Nikolov. Okay, Thomas, actually it is not Thomas also, it is Tomas. I think it's a Mexican word or something like that, Spanish or Mexican. Tomas Nikolov at Google in 2013 is what the word to vector was actually, the foundation was actually laid. Based on this only, Google has built this concept of transformer from their bird, everything he has developed. His, the foundation, or I would say his, his pillar for, building that kind of foundation is this concept of in the word to vectors in the word embeddings. So next is context based learning. Now suppose your corpus includes the king rules the kingdom, right? The queen governs the empire. Now word to vector will learn that king and queen appear in similar context, so their vectors are close or close by. So king and kingdom often co-occur, so they have strong association or they have strong correlation among themselves. So what makes word to vector special? Now, by this time you would have understood what makes word to vector special already, right? So they can capture the relation. So if you give a particular word or a words, right, their relationship is understood very easily, right? For example, the vector arithmetic here, the math behind how the vector actually runs. For example, king minus man plus vector woman. So here we are subtracting, or it is not a king, it's not a man. That means he cannot be a king. So definitely it's a woman. So there is a high chance that the person is a queen. So this ability to compute analogy like relationship is what I told because this AI itself is based upon the logical reasoning, right? So that is why it is able to compute the analogy, and like relationships is what makes word to vector more powerful. Now here, to understanding the embedding space, so let us imagine that there are 2D or 3D plots, right? So here you can say king queen, monarch, right? So all in a similar, I would say similar kind of grouping, right? So far apart, king and banana, right? Just for an example. So words that appear in similar context are closer in this embedding space. So this, this vector space, what we are talking about is something where these words are actually clubbed together, which are very similar in nature. Now, what are the advantages? So you can, by this time you would have actually predicted what can be the advantages, right? So semantic similarity. So identification between, similar words is possible by using this word to vector. Then dimensionality reduction or reduces the dimensionality compared to one-hot encoding. Then enables word analogies and clusterings. So similar kind of words are clustered together. So this can be implemented with using the all deep learning models. Now, let us see what is, how this NLP is actually linked up to deep learning part. Okay. So this entire deep learning structure is actually based upon the neural networks. Now, things like text classification, machine translation, named entity recognition, question answering, summarization, text generation, everything is basically linked up to the deep learning part of NLP. So what are the key components we have already seen, right? Important concept you have seen, which is the word embeddings, right? So this basically transforms into continuous vectors. Okay, so word to vector and glove. Now here there is one more concept, which is RNNs. Okay, so these basically RNNs are used for sequential data. Okay, and there are variants of RNNs, right, which is LSTMs and GRUs. Okay, or you can say gated recurrent unit, and as well as LSTM, which is long short term memory. Now these two are very important, right? LSTMs and GRUs. So we will see also the practical part of LSTM as well as GRU as well. Okay, so these are a bit of advanced concepts, but okay, even the transformers is advanced. So but still we have to go through the practical part as well, correct? No, so try and understand how things work in the generative AI. So so we'll see the LSTM part as well as the GRU part as well. So next is the attention mechanism. So this is what I was actually trying to tell you. So help models focus on the relevant parts of the input. So that is why they are called as attention mechanism. That means the attention is given to what is required in that particular aspect. So improves performance in translation, summarization, etc. Now after this, first the word embeddings have been started, then RNNs have been started along with that. Then we had the attention mechanisms, right? Then we had, right, in 2017, which is transformers, right? So in the transformers, we had the GPT models and the BERT models. So this is basically self-attention plus positional encoding, enable parallelization and context understanding. So, from step 1 to word embeddings, it went to step 2, which is RNN. Then step 3 was attention mechanism. Then the step 4, what we are in, is the transformers. Okay, so currently we are living in the 4th generation, I would say, or you can say 4th component of deep learning. So, and the thing is, each thing, for example, the initial step was word embeddings, correct? No, so then it came RNNs. So RNNs are completely dependent upon word to vector and glove. You cannot ignore word to vector and glove and go to RNNs. So LSTMs and GRUs doesn't exist without word to vector and glove. The same way attention mechanism cannot exist with word to vector, glove, LSTM, and GRU. So it's like a chain of, the problem is that, so you cannot just, okay, fine, the current thing is transformers, so let me directly learn. No, it's not possible like that. Actually, the concepts are, linked with one another. So that is the tricky part actually, to break through. And next is the transformers part. So yeah, after that, this transformers has been linked with all the other things as well. So what are the applications of this, core components is voice assistants, machine translations, search engines, what we are using kind of right now, chatbots, text analysis, fake news detection, and so on. So challenges, there is always a problem with ambiguity in the language, right? So contextual understanding is has always been a problem, but that has been tried to rectify so much, right? And huge documents, context understanding has become a bit of problem, but in at some level it is trying to be addressed and trying to be the research is actually happening on that part as well. Okay, so final thing what I want to tell is basically NLP in deep learning is at the heart of many AI powered applications. So with models like BERT, GPT, machines are becoming increasingly proficient in understanding and generating human-like text. Mastery of NLP with deep learning opens doors to developing cutting-edge applications in virtually every domain. So we need to have the understanding of NLP along with the deep learning technologies, and then we can actually use the AI-powered applications in a smoother way. Okay. So the next thing is, let us see what is RNN and all, then we will go to the practical part. Okay, LSTM we can cover later. If possible, we will try that. Okay. Right. So now let us understand what is ANN and RNN. Okay, in a simple way. So basically, ANNs are nothing but the neural networks or artificial neural networks. Now, I'm not going into very deep because if I have to talk about ANN, bigger pictures and all, it takes a lot of time, lot of understanding. We need multiple, examples, pictures, and all. So that takes a lot of time. So I don't want to, spend a lot of time on that part because we have so many other things also to do. So let us try and understand this ANN in a very simple term. Okay. So ANN is nothing but a network. Okay. So what kind of a network? It's a deep learning network. Okay. So deep learning or deep in deep learning indicates the depth in the number of layers in a network. For example, if the layers are 10 layers, 5 layers, 4 layers, 6 layers, 100 layers. So how much of depth is there is what the deep is basically about. Okay, I would say layers, or there is also a technical term called as hidden layers as well, because that layer you'll not be able to see with your naked eye. That only the compiler will be able to actually compile. Next is basically these ANNs are used for classification. Actually, they are used for everything in current day scenario. I would say not just one task or two tasks, right? There is a lot of areas where these ANNs are used. The biggest challenge what happened with the ANNs is ability to handle a continuous sequence of data. So that is where the concept of RNN came into the picture. That is where the concept of RNN came into the picture. So this RNNs has led to the development of LSTMs and GRUs. Okay, because something which has some limitations, right? Definitely they will try to upgrade. Correct? No, they will try to improve. Obviously, correct. So that is what exactly happened with the ANN also. So a new advancement in ANN came, which is RNN. So RNN is nothing but recurrent neural networks. This has the ability to handle, I would say, a data which has, or a data which is in a continuous form, right? For example, like a text data, right? Something which is in a continuous form or can be written continuously. So that, or I can say another word is the sequential form or sequential data. So for that, we can say that the thing like text data. So for that, they have developed a concept called RNN or recurrent neural networks. Now let us go to the memory capability. Now, there is a negative part which ANNs cannot handle. So that is why RNNs have kept good. So why the most biggest reason is the ability to keep the things in memory. This is the biggest problem what ANN has faced. Okay, so it cannot keep things in memory. Okay, so there is no concept only of memory, so things cannot be in the memory. So understanding the previous uh, input and processing on that has become very difficult. So that is where the RNNs have come into the picture. So RNNs have memory state, which is a hidden state. So even the RNNs had a problem. Okay, so one biggest problem is the vanishing gradient. Okay, what is vanishing gradient? In a simple terms, that the term which is supposed to be existing is after applying derivatives, or you might be knowing, you would have done derivatives, because deep learning is completely math. So it's like completely derivatives and all these things, partial derivatives, full derivatives and all. So what happens basically is, in a simple term, I'll just tell it in a simple term. So what is happening is, if you try to derive or find the derivative of something, it should not become a zero. It actually has to convert to something. So instead, if you are applying based on the circumstance, what is happening is it is going to zero. So that is basically a problem of vanishing gradient. So that problem has been overcome, or that problem has been addressed in a very important development in history, right? That is LSTM. So LSTM is long short-term memory. So what this will do is, it will keep the things in memory for a long term, right? Or I can say a long period of time, till where it is important. After that, it will leave it. So that is why the name has long, short. Both are there. See, that is why. So it will remove from memory if it feels it is not required, or it will keep in the memory till it needs to process something. Okay. Now, this LSTMs also has a few problems. Okay. So there is one more method, right, which is GRU. This is basically a simplified version, right? This was giving gated recurrent unit. We will see this also in action. So this was giving actually a some more better performance compared to that of normal LSTMs. Now, so RNN you have already seen. So RNN is nothing but the sequence of neural networks which is defined for, or which is designed for text data. So like a speech, time series forecasting, something happens with time, a sequence of things which happens with time, like this, like the time series data, right? So in statistics you would have heard time series data. So for that, so right, so before going into LSTM, so first let us understand that what is this TF-IDF, and then the concepts of we'll apply this word to vector and all those things, and then we'll go into that part. Okay, so let me share the practical part. So then we can go to the LSTM. Okay, just give me a minute. Just give me a minute. I'm just compiling this. I'll just share my screen. Just give me a minute. Because in I think you would have probably known this collab. Every time we open, we need to compile. There is one big bummer what we have. Yeah, I think it is done. Glove. Okay, fine. I'll just okay. Fine. First, I'll share this TF IDF. First, we'll see that. Later, the other things I'll compile it later. Okay, let me share my screen. Okay, so I think you can see the screen, right? Okay, so first let us see this TF IDF, and then we'll go to the word to vector. Then we'll go to the glove. Okay, so these three, we'll try to understand that first. If you're able to finish that, then we will move to, we'll move to the LSTMs. Okay, based on the time. Okay, because this TF IDF also requires a lot of understanding. So let us. Okay, please let us go step by step. Okay, so today I've added a few comments. So now, first let us try and understand this TF IDF concept. Okay, we can actually implement this TF IDF using a particular module, or I would say a particular function, which is TF IDF vectorizer. Okay, so if you see, okay, so what I will do is this one, I'll run it again. Okay, because it's which run it again. I think it's fine. Okay, great. So yeah. Okay. So anyway, I've executed again. Fine. Now it should be fine. Okay. Now we are using the function which is TF IDF vectorizer. Okay. So what I will do is probably this is actually not helping you. We'll just put here. See, basically, what is the here it will have a hyphen. Okay, now you can see the difference. Okay, so TF IDF is the concept. Okay, and vectorizer is what it is actually embedded. So actually, this is a continuous function. So here you cannot give a gap. So that is why in the comment I have mentioned, so that you can understand that what is this function which is there, because it's basically a continuation TDF TF IDF, no? So it looks like some function, so it is not. It is just the concept which is TF IDF, term frequency, inverse document frequency, and the vectorizer, because the concept is a vectorizer concept, no? Which basically creates into a vector. Now, so this pandas is nothing but the pandas library, right? And this TF IDF vector, or we can say the function, is inside this feature underscore extraction module. Okay. Now let us use one corpus or a text. So the text what we are using here is ChatGPT is a great chatbot developed by OpenAI. So ChatGPT helps user with a wide range of NLP tasks. Natural language processing is a crucial part of AI. Machine learning and NLP are transforming the technology. So this is what the corpus I have taken. Now let us break here into a few things. There are only there are only four lines of code, but so much of comments, right? So it is for you guys. So this is 1, this is 2, 3, and 4. This is only the 4 lines. Okay. Now the next thing is applying the TF IDF vectorizer. Okay. So here you can see that I'm applying the function. The most important thing is I have to apply the stop words, right? So these words like is, right, of, are, and by, all these are stop words, right, which are not required and which doesn't have much of importance. So these stop words have to be removed first, right? So for that we are applying the vectorizer. Okay, so we are applying the stopwords function first. Okay, let's put like this, maybe in one, or else too much of like no. Now it looks bit less. Okay, so first thing is removing the stopwords. Okay, and after that removing of stopwords, the next thing is fitting using the vectorizer dot fit function. Okay, now we use this vectorizer dot fit, but we don't just fit the data. So yesterday also we have seen the similar kind of concept. We don't just fit, we transform as well. So we use fit underscore transform. Okay, so this transform will transform as a matrix, right, creating a sparse matrix. And this fit will learn from the vocabulary or try to understand or build the model. Okay, after that the next thing is, the most important thing is to array. So this to array function also we have seen. The output will be transformed as an array. That is why we are using this dot to array as well. Now the next thing is here, yeah, you already know this. What is this data frame and all? It's kind of a table format. So then to array done, and what is the next function? So here we have the get feature. So get feature is nothing but actually giving you out the names. I think even this function we have used yesterday. So this is not a new function. So coming to the next one, this will actually give you the output in a meaningful way in the form of the, I would say, probability, because the scores what you are getting outside is a probability score. Okay, so for that we are actually rounding it. Okay, or we are creating a output. Okay, now let us go to the again once. Okay, here I've given dot round. No, that is just for rounding the values to 2 decimals. If you change it to 3, or if you change it to 4, something like that, you will get 4 decimals or 5 decimals based upon what you have actually rounded. Okay, so next thing is the same thing. What we are going to do is we are trying to identify the top 5, okay, by probability. For example, if you have to identify the top 5, we can give n is equal to 5. So we can define the function. This is basically giving a user defined function. Okay, so I think you're aware of bit of Python. Okay, I hope you're aware of. So ilog is nothing but that particular columns you can identify by using the ilog function. So here it is, we are asking it to give the top 5, and 0.46 is the top probability what it has. Okay, now let us go to the next part. Here let us try and understand on the bigger corpus or bigger text. Okay, so let us try and identify on the bigger corpus or bigger text. Okay, so here we are identifying, we are also visualizing it. Okay, so I have built, or I have actually I would say brought in matplotlib as well. Okay, along with pandas, numpy, and this tf-idf vectorizer as well. So this sns.set probably you are seeing for the first time, maybe, or you would have used, right? This is just used for grid lines. Okay, now let us go to the corpus, or let us see the text. Okay, so here you can see natural language processing is a subfield of linguistics, computer science, and AI concerned with the interactions between computers and human language. It focuses on making computers understand, interpret, and generate human language in a valuable way. So like that, I have given on the machine learning as well, how it is and what are the applications, and despite advances, NLP still faces challenges such as context sensitivity. So that has always been there. So how many models are coming up, but still context-based understanding is what machines are still lacking. when we are using it in generative AI. So that is one of the issues as well. So this is the bigger text what we have given, and the same way what we have actually applied, right? So we are actually asking that as well. Now let us see that here what I am doing is, so first is I'm initializing the vectorizer, right? And the next part is I'm removing the stop words, right? And I'm using English because it's an English language. And here I've given max underscore df. So this one we did not give at the previous one. So what this does is ignores terms that appear in more than 85% of the data. So the maximum uniformity or filtering we have given at 85%. Okay. So next is smooth IDF. So this smooth IDF is nothing but it helps to smoothly process the documents, okay, or to find the rare terms in the document. Okay. So next is applying the TDF. We use the vectorizer dot fit underscore transform. This is not a new thing which you have already seen in the previous code. And here creating to the data frame, right? And next thing is rounding it off to 2 decimals. So you are getting the list of the probabilities. Okay. Now for that, asking the top 5 probabilities, what it is there, top n, which is 5. Okay. So what happens? It will give you the top 5. So here you can see the top probability is 0.23 is the maximum probability. So next thing is, after that, what we are trying to do is we are trying to plot the graph. Okay. So I'll just show here. So here we are trying to plot the graph. That is why we bought in the matplotlib. Okay. So what I'm doing is for all the documents, I'm plotting the graph. Document 1, document 2, document 3, document 4, document 5. So for the first document, the word computer and human is repeating multiple times. Okay. So you can see it here. What I'll do is I'll just scroll it like this. Yeah. Okay. So that is what in TF-IDF score also, it is around some 0.36, 0.37, something like that. And for the second document, better is basically around 0.25, right? And for the third document, it's almost again the same, 0.25, something like that it is coming. And for the fourth document also, it's around some 0.25. Fifth one is also the same. Okay. So like that, we will get the TF-IDF score. So this TF-IDF score calculates the probability of the a particular word occurring, the chance of that particular word actually occurring. So it's a very important, actually, it's a very important concept, in generative AI. Okay. So that is what is about TF-IDF. If you have any doubt, you can ask me. Okay. So I'll be answering your questions. Probably after the break, we can touch up the concept of word to vector. Okay. Word to vector, I'll try to simplify. This is actually a bit of complicated kind of model. We use the spacey model. Okay. So in the meanwhile, I'll also restart the word to vector. So probably you can ask questions if you have in that meanwhile. I have to restart the session and I have to run. These are a bit of complex models actually from this word to vector. Till this TF-IDF, it's a different ball game. After that, from this spacey, using spacey for running this word to vector glove, attention mechanism transformers, it's actually a bit of bit of some headache. Okay, because it takes a lot of time to run, compile, all those things. Okay, so probably you can ask. I just restarted my sessions again. Anyway, I'm just running it again because however I run again, but still it will. If we need that running when we are actually learning. So yeah, probably you can ask questions in the meanwhile. Okay. This is happening. I'm just yes. Okay. Great. So word to vector, it is ready. I've just ran it. DF, IDF. So DF, IDF, I'm sharing it in the chat. Okay. Yeah. So this one I've shared. So yeah, this word to vector and glove we will see. Okay. Just restarting this anyway. Okay. Fine then. If you don't have any questions, I'm just waiting for your questions, guys. Simultaneously, I'm running this anyway. Okay, then if you don't have anything, you can go for a short break. Okay. Okay, so no questions. I think you're fine, maybe, I guess. Okay, so then let us continue. Okay, so then let us continue with the practical part of word to vector and then glove. Okay. Let me share my screen. Okay. Okay, so I think you can see the screen, right? So for implementing word to vector, okay. So this is actually using Spacey, okay, right? So Spacey library. I'll just write Spacey, no issues. I don't want. I know it's a library. Okay. So this is basically using the Spacey library. Now, the first important thing here is, just give me a minute. Okay. The first and foremost important thing basically for this is first to install the Spacey. Okay. So I have because there are a lot of things when it comes to Spacey. Okay, so the Spacey is a very vast and a very important library. Okay, so this basically has a lot of things. So here see just to I've already ran it again. Okay, it's already installed, but I've ran it again. But just to show that requirement already satisfied, it has given a big line. See, so in this you can see this lang codes. Okay, these are for lang chain. Okay, so this is basically a very big library and a lot of things are there, okay, which it actually has installed. You can see it here. Okay, now so that is the foremost thing which you have to actually check first. Okay, anyway, I'll share this. You can actually try and rerun. Okay, now going to the next part, we have to download this core SM, okay, package. Okay, and this package will download here. Okay, so this is one thing. Now after that, the third important thing what we have to do is we import the Spacey into the collab, right? And then we use the Spacey model. Okay, and here I'm giving a very small sentences to understand because the processing will be very high. Okay, so I would say that using a small sentences to understand is very important. Okay, probably if you want to know more about word to vector and glove models. Anyway, in attention mechanism and attention mechanism and transformers, what I thought is we can actually I would say we can actually do bit of more level, we can go up a bit. Okay, so that is what I thought because since things are running on transformers, so it will be very easy for you to link up also with the real world things what is happening. Okay, so we will see at bigger I'm planning for that a little bit bigger level on transformers and attention mechanism. So we'll keep it very simple for this word to vector and Spacey. Okay, using the Spacey library. So now let us take a few sentences, which is this is a great day. It's a wonderful day. Okay. Now this is applying the NLP. Okay. So let us we'll remove this. Okay, just give me a minute. So this basically this model you already know. Okay. This is a Spacey model which you can or which you have to load. Okay. Okay. Now the next important thing is, okay, so this one we can remove. Okay. Yeah. So let us see the vectors for the word great and wonderful. Okay. Now let us print the first important, or you can say the important function what we are going to use is similarity between the vectors or sentences. Sorry. And for identifying that, we are using the similarity function. Okay. I will just select this function. You'll be able to see. So this, see what it is telling you. So make a semantic similarity estimate. The default estimate is cosine similarity. Okay. So this cosine similarity is what basically it will actually use. Okay. For example, I will mention here. Okay. So it is basically using the cosine similarity. For example, if you want to understand what is cosine similarity, you can also bring in Gemini here. Okay, you can just put cosine similarity. It will actually give you what is cosine similarity as well. It's working on that. Huh. Okay, so a simple definition it has asked given. Okay, so probably we can put it here. Okay, the sentence is big. What we will do is lower them. Wait. Okay. It's too bigger a definition, but it's okay. It is very important actually to mention here. So, okay. It is also, no, I don't want this. Yeah. So let us try and understand what is this cosine similarity. So this is basically a measure of similarity between two non-zero vectors of an inner product space that measures the cosine of the angle between them. So it is often used to measure document similarity in text analysis. A cosine similarity of 1 means that the vectors are identical. 0 means they are orthogonal, which is zero similarity. -1 means they are diametrically opposite. Now, I know that this part will be a bit of difficult for you to understand unless you are from mathematical background, because there are concepts like, in linear algebra, like inner product space. Okay. So this also comes under, orthogonal, and then, I would say vector space and all those things are there. Okay. To understand this concept in very detail, you need to understand that. So probably you can try and go there to understand a few things. Okay. Right. So now focusing on what is easy for you to understand is this. If you get the value of 1, it basically means that the sentences are identical. This is an easier way because the output is that. So if you want to dig deep, probably I told you, you can understand or do more research on linear algebra and understand these concepts. That's up to you. So here 0 basically means that there is no similarity, and -1 means they are opposite in nature. Now here what we are trying to do is we are trying to run the output. Now when we run I'll again run this later, okay, because I've changed a few things. I have to run it again, but anyway output is there. We will see the output. Again, it will take a lot of time because a few things will actually take a lot of time to run. Okay. Yeah, these are not, this deep learning and all, they require a lot of GPU computing and all. So it takes a bit of time to run. Okay. So leave that. Now here, if you see, each vector for similarity has given a value, the cosine similarity. Or for for the word great, it has given. Now for the word wonderful also, it has given the vectors. Now between the sentences, there is a similarity of 0.92. Okay. So this 0.92 indicates that it is close to 1. That means these two sentences are identical. Okay. Almost identical, because it is not giving 100%, but it is giving around a probability of 0.92 or 92.32%. So now see the words, see the sentences. This is a wonderful, it's a great day. It's a wonderful day. Now imagine that these sentences are big articles. Now you can understand the use of this model word to vector. It will give you that, right? It will give you the, wait. So here I will remove. Okay. So now you can imagine that how much of, how much this generative AI models are helping you to understand. It will find the similarity. Correct now? Yes. The same thing here. We will use one more model. Okay. Right. Here we have downloaded the small model. SM is for the small model. Okay. SM is small model. Now let us go to the another one, which is medium. Okay. So MD is nothing but the medium model. Okay. Now let us try and understand by what the medium model does. Okay. Now let us import. Okay. I've added the comments also. Okay. Now let us try and understand the other things. Right. Now here, if you use here, let us try and find with the similarity between words. So king and queen. Okay. So if you try to find the similarity between these words, the similarity score is 0.38. That means they are completely, right? They are not different words completely, but the similarity probability is also very less. Okay. Now let us go to the next level. Okay. Let us give a few words here. Okay. So I'm creating a list of words to understand. I'll come to this TSNE bit later. Okay. Now first try and understand. I'm giving a few words like king, queen, man, woman, apple, banana, car, bike, computer, and science. Now I am trying to build a model, okay, using this spacing. Okay, where is this? Where to show? Using this spacing. Okay, so I'm using this spacing. Now, what is this TSN here? I have mentioned. I'll show you. Let's go down. Somewhere I've mentioned here. Okay. Probably I'll do one thing. Just give me a minute. Okay, sorry, I thought I mentioned here. Okay. Fine. What we'll do is we'll just take the help of Gemini. Okay. No problem. It will give us TSNE. Okay. We can actually put boards. Again, it has given big definition. Okay. I'm looking for a simple definition. Okay, fine. What to do? I will just post it here. Okay, no issues. We'll just try to compress it into at least some 3 words. Oh my God. Okay. Just give me a minute. It's too big. Okay, finally I brought it to 4 words. Sorry, 4 sentences. Okay, right. So let us first try and understand here what exactly I'm doing is I'll come to this. I've given some words and I'm actually trying to build a model. Okay, and I have given the words. So these things are not new actually. You have seen these things what we have actually done in the previous things also. Now to use this TSNE model, okay, this we basically used for medium to high range sentences. Okay. Now, what is this exactly? TSNE is. It is basically I would say in a simple terms, it's basically a statistical concept. Okay. So this first thing you have to understand is SNE. Okay, this is very important. Okay. Now, in the previous one, we have seen a few models. Especially I would just I'll show you. I'm going back. Where is this? Where is this? Here I think we have used correct. Similarity. Yeah, I have mentioned here cosine similarity. Correct now. So this cosine similarity can be used for particularly smaller models. Okay, not for very high. This has bit of mathematics involved in it that I already told you. Now the problem is it gets even deeper when we are using medium to high models. So what will happen is this uses a technique called as stochastic neighbor embedding. Okay. Now let us try and understand by breaking it down into pieces. Stochastic is nothing but a random. Okay. So it tries to identify the random neighbor. Okay. Embedding, you already know, finding the relation. Okay. Now, let us forget about what is the definition, what I have put. That is what Gemini has given, I have put. I have not even read that. Just I casually have put. We'll read it and we'll try to understand. But what exactly is this? If you break down, so random neighbor word context or word relationship. That means randomly you're trying to pick a neighbor and trying to find the relationship with that particular neighbor. That is what SNE is basically. Now T distributed. Here comes the bigger problem. Okay, so randomly you cannot do like that. Okay, even though the model tells you that, right? For that we are using a certain T distribution or a T distributed thing. Now what is that? We will see the definition in more detail. Now I have seen, or I have actually come across a very good, probably I don't know how much of you are aware of that. There is a concept called as dimensionality reduction technique. So dimensionality reduction technique is probably, or it is a very important concept which is basically used to reduce the dimensions of the data set. Okay, so these are basically done, right, focusing on the higher dimension, for example, which has more variables, right, understanding them and trying to reduce the size will actually help you to create the model in a easier way. Now it aims to preserve the local structure of the data, meaning that the data points are close together in a higher dimensional space are likely to be close together in the lower dimensional space in visualization. This makes it useful for exploring blah blah blah. It's just a random textbook random textbook definition, I think. Okay, so I think this definition will not help you that much. Okay, fine, let it be. I just put it for Gemini. Probably I could have taken it from ChatGPT or something like that. I could, maybe Gemini is not giving that great definition. Okay, chhod de. What exactly this does? Let us keep it in a simple way. Okay, let us not think too much or complicate too much. Now, what this actually does is, it's a reduction technique where it will first try to reduce the size of the variables. From there, it will visualize and try to understand that what neighbors are having more relation with me. That is done by the concept of TSNE. That means it tries to find the relation of neighbors first by reducing the size of the I would say attributes or variables. That is in where this TSNE, I really love this TSNE concept, right? It's this, a function. It's a very, great, one of the great concepts. Probably if you're more into data science and generative AI, probably you might understand what this fellow is speaking, right? So this TSNE function, right? It's inside the manifold module. Okay, so manifold, it's a module. This sklearn, I told you, this will show as module. This is one big bummer. sklearn is nothing but a library. It's not a module. Okay, so manifold is a module. That is correct. Okay, this TSNE is a function. Okay, here it is giving. See, thank God, it is giving as a function. Here it is giving more better result in Colab than we have taken in Gemini. This is what I just wanted. See, TSNE is a tool to visualize high dimensional data. Okay, this has given that only. It converts similarity between data points to join probabilities and tries to minimize pullback labor divergence. KL divergence we have seen, we have discussed, no? That only is this. Between the joint probabilities of lower dimensional embeddings and the higher dimensional embeddings. So TSNE has a cost function that is not convex, that is this fellow has gone more technical, which will be a bit difficult for you. First, you have to understand what is the scale divergence, what is convex, what is cost function. So let us not touch that much. But in a simple terms, I think I have told you, right? This is basically an embedding technique, or embedding is nothing but finding the relationship between the words. So first of all, what will happen is it will remove this lower dimension words which have relationships. Okay, so focusing on the higher dimensional space. Okay, I think probably bit at least you would have understood. Yeah, this models now from word to vector will become more complex. Be ready for that. That I will tell you. So word to vector, glove model, attention mechanism and transformers. These though next level, because these are like 4 pillars for generative AI. So they are holding this generative AI in a bigger way. So now let us go to, I think probably you would have understood a bit at least on TSNE, T-distributed stochastic neighbor embedding. Okay, probably you would have got it. Now let us go to the next part. So here I am applying the TSNE function, and here, yeah, it is showing, see, here it is showing the number of components. Okay, how many parameters you have. Then the random state. Random state is nothing but the fixed random sampling. So if you give random state of 42, the random sampling will be fixed. Okay, so how many times you do the sampling, you will get the same samples. So perplexity is, here I'll show you, right? So perplexity is nothing but actually it will try to fix on that. So number of iterations I'm giving 250, and here I'm fitting the data. Okay, so now you can see the original words and reduce number of words. Okay, so this is the main I would say main agenda of using the TSNE function. Okay, now after using that, let us try to visualize the words. Okay, using a matplotlib function. Now you can see that the words, how they are visualized. Okay, based upon them. Now here there are some key findings what we have done. Okay, now the similarity score between king and queen are actually I think around some 0.38 we got, right? So 10 word vectors were extracted, each with dimensionality of 300. So TSNE dimensionality reduction successfully transformed 300 dimensional word vectors into a 2D transform or a representation. So 2D scatter plot was generated to visualize the reduced words, right? This is what we can. So this is just a simple model what I have built. Okay, so it gets more complex if you go into more. It will be a bit difficult for you to understand. So I've kept it very simple. Okay, so on more, if you want on word to vector, we can concentrate, but I don't think you need it, because what will happen is when I cover glove, when I go to attention mechanism and then transformers. So those are actually built upon these only. So you will be understanding this word to vector also in a better way. Okay, so you need not break your head on this. Okay. So I just restart and run this again, because just give me a minute. because I've done some modifications. So this will probably try to run this again, and then I'll share this. Okay, then I'll share this to you. Okay, so just give me a minute, let it run. Here you can see that it is executing. Okay. Yeah. So what will happen if I try to run, one more now? This will slow down. It will take time. So we can just wait for a bit. This will run. Okay. It will run fastly only. Smaller model, bigger model, medium model we have run. Okay. So see the compilation. See how much time it's taking. Okay. So yeah, you can also, anyway, in sharing the files now, you can import or open by putting it in, and you can run. Okay. Yeah. So that part takes a bit of time, and I think this is fine. Okay. Yeah. So after running this, then I just want to download this. Okay, because I have to share to you now. Yeah. So it is saving here. You can see. Then I can close. Okay. Now let us go to the next part, which is glove. Okay. So we have seen word to vector, right? Now let us see the concept of glove. Okay. Now this glove. Okay. So what I'll do is here. Just put glove word embeddings. I'll just remove this name. Okay, this should help you. Yeah. Now, for running glove, the most important thing is keras.tensorflow. Okay, or tensorflow.keras. So what I'll do is I'll just okay, I'll just put it here. Okay. So Keras and TensorFlow are basically a deep learning library. Okay. Now we'll just put what is basic. Okay. We'll not touch up on things which are bit advanced. We'll just put what is there. Okay. I think they should be fine for you. Okay. This is enough. So this TensorFlow is basically a library. Okay. So what I will do is I'll just put it here. Is a library. Okay. And this Keras is a framework. Okay. Framework. Yeah. So this is basically a framework. Okay. Now this Keras, this tf.keras, what we are using, tensorflow.keras, this is basically used for developing high-level APIs. API is nothing but application interface. Okay. So this is basically used for developing high-level APIs. Now, yeah. Now here you can see that we are trying to train the neural networks. That's why this glove concept is about. Okay. So glove word embeddings. Now here, let us start with the pre-processing, what we have given. Okay. This tokenizer, I think you are aware of, correct? And then let us use this sequences, padded sequences. I'll come to that. What is this padded sequence? Okay. So I'm giving a sentence. I love deep learning. I love natural language processing. Deep learning is fun. Natural language processing is amazing. I love machine learning. Machine learning is the future. So I've just given us some random sentences. First, what I'm trying to do is I'm trying to attendance link. I don't know. Just wait. I think sir has not posted it, I guess. Not sure about that. I just posted it. Sir will give. Don't worry, Aaron. Okay. Okay, so you can concentrate on the concept. Now, from this example, or we are trying to tokenize, okay, what we are actually doing is we are basically, finding the vocabulary size here. We are not asking for tokenizing the words. We are just asking to put into tokens. How many tokens or vocabulary is there? Vocabulary size. So here we have a vocabulary size of around 15. Okay. Now, this is one thing. And to use this, uh, you know, glove, we need one important download, which is Stanford. Okay. This has this glove. Okay. So that is why I have put it here. Okay. So here, this will download. I think you are aware of that Stanford University, right? Those are the people actually who developed this glove concept. Okay. So when you if sir has posted, you can just mark your attendance. Okay. Yeah. So here, if you see, this is actually downloaded from the Stanford, and here you can see that it is downloading a few things. Okay. So if you see here, the file what it has downloaded, it's around some 822 MB. So it take 2 minutes for me, 2.5 minutes for me to download. So you require an internet connection, good internet connection to download this, because this Stanford.edu has the data which is required to process the glove. Okay. So I told from this, this word to vector, things will become more difficult and tricky as well. So here we are downloading from the Stanford University website. This is the links for that. Okay, so you need not worry. I have mentioned everything in my Python notebook. Okay, now going down, we are loading the words. Okay, so they are totally of 4 lakh words in your Stanford University. What you have downloaded. So here you can see loaded glove words. Okay, it is around 4 lakh. Okay, now in that 4 lakh words, what we are trying to do is, I'll just show you. Okay, this is basically a standard syntax. You can just get it from Google as well. That is not an issue. What I'll do is I'll just go down to show you what exactly I'm trying to do. Okay, now here I am trying to build a model. Okay, from the words what I have used. Okay, so now this index what I have given here, that I am using. Okay, now for building the model, we need the model function, right, or the module which is inside TensorFlow and Keras. So we are importing the sequential model from the models, and from the layers we are importing embedding, global average, pooling, and dense. So dense is for identifying the depth of the layers. So that is what we are giving here. Here you can see the activation functions. The activation functions are nothing but functions which are let me okay, I'll just show you what are these. Probably this definition can help you. Okay, so what are activation functions? These are actually statistical functions which are used to connect from one layer to the other layer. Okay, so here okay, let's see what this has given. Okay, okay, now they are actually very complex components, and the main important thing of this activation function is bringing the non-linearity into the picture. Okay, so bringing the non-linearity. So I think you guys know that what is linear and what is non-linear. Okay, I hope you know. Okay, so linearity is nothing but something can be put into a straight line. Okay, so that is linear. So non-linear is something where you cannot put it in a straight line. Okay, so most of the data what we are using is kind of non-linear. Okay, so that is in where this neural networks are extremely useful, I would say, or extremely more practical in the real world scenario. Okay, now to identify the non-linearity, one such functions or one such mathematical and statistical functions which we use is the activation functions. So these activation functions can capture the non-linearity in the data. Okay, so that is the greatness, I would say, using a activation function. So there are a few activation functions like the ReLU, sigmoid, right? And I think my Gemini model also has given that. I just put this rectified linear unit and sigmoid. I'm not going to post these. You can just Google search it later. That's not a problem. Okay, so the two activation functions what I'm using to build my layers is basically the ReLU and the sigmoid. So there are other functions like the tanh function, right? A leaky ReLU also. Like that, we have multiple functions as well. And coming to the loss function, so loss function we have something called as entropy model. And for metrics, we use the accuracy. And the most famous optimizer, what we use is the Adam. Okay, so Adam optimizer is a very, I would say, it's a very important model, or I would say function. Okay, so Adam full form you need to remember or to understand. I don't know what it is giving here. Adaptive momentum, something will be there. It is given here. Adaptive learning rate. It's Adam. Yeah, this is what I want. Just want this. What I'll do is I'll just put it here. Okay. Okay. Adaptive learning rate optimization algorithm is what Adam basically is. Okay, that is enough. So that is what I'm running here. Okay, so here it has built a model. Okay, here this basically epochs. Yeah, this is epochs is very important. Okay, to understand what is an epoch in a simple language, epochs are one. I will not say epochs. Epoch. Actually, epoch is a one complete cycle of training data. Okay. So one complete cycle of training data is what basically an epoch is. Okay. So here number of epochs is 100. So usually in real-time projects, we use more than 1000 epochs. Okay. Because more the number of epochs, more the data is able to fit in. Okay. Or the accuracy will be good. Okay. So more number of epochs is very much required in order to train the data more. Then we are predicting the loss function using the training and testing mechanism. Then we are predicting the output. Okay, so that is what the predictions, what we are actually done. Okay, so this is a simple way to implement the GLUF. It's not a complicated thing what I've done. It's a very simple thing what I've actually done. So this is what it is. Now what I'll do is I'll just run it again before sharing this Python environment for you. Okay, so I wanted to restart and run it again. Okay, so in the meanwhile you can just ask me any questions if you have. Okay, So we have 5 minutes left. So if you have any questions, you can please just let me know, or else we can wind up after 5 minutes. Okay. So it's executing anyway. I'll share this once it is executed again. Okay. See, this one is downloading. See. Got it? No, this will take a bit of time. Okay. In the meanwhile, you can ask. I'm executing. So Glove anyway, if you want to implement Glove, you have to download this zip file and you have to run. There is no other option actually. Okay. So as posting attendance, you can just answer posted, man. It's posted. No, we can copy it and I can put it here. No, not able to copy. It's posted, Harish. You can just check. Okay. Yeah, let it compile in the meanwhile. You can just post your questions. We'll see the LSTMs. That is one heck of a concept as well. LSTMs, attention mechanism, transformers. Oh my god, yeah. Well, they are like lifeline to generative AI. This part executed. See, these are taking a lot of time to execute. It will take even more when we go a bit further also. Yeah, start. Good. Okay. So I think just download the file. So I'll share you this. I think I've shared you the TF IDF. Along with that, word to vector. Why? I'm not able to share. Okay, now it's coming. Word to vector and then glove. Okay. Glove word embedding also I've shared. So word to vector and glove, both I have shared. Okay. Yes, Amar sir, we can wind up. I think no questions as well. I've shared the files also.
Okay, yeah, sure, sir. Thank you.
Yes, yes.